Welcome everyone. In this lesson, we're going to be looking at double integrals, and we're going to extend the definition from double integrals over rectangular regions to kind of general regions, more general regions. And to see how we're going to do this, let's kind of take a look at the setup here for the types of regions we're going to be trying to integrate over. And so we're going to have a function little f, and we're going to be looking at a bounded region D. So again, when we say this word bounded, what do we mean? Well, it means we can enclose it with a circle or a rectangle. So that's what we want to think of here. For a bounded region, it can be enclosed. And let's do a rectangle, because that's going to extend nicely from our rectangular definition of double integrals. So we have our region D here that's sitting on the xy plane, and this is the region that we want to integrate our function over. And what we're going to do is we're going to look at that region D, but we're going to enclose it with a rectangle R. So completely surround it with a rectangle R. And what we're going to do is we're going to be, really our goal is to just integrate the function f of xy over this bounded region D. What we're going to do is we're going to cook up a brand new function, which we're going to call capital F of xy. And the way we're going to define this function, this is going to be a piecewise function, and we're going to define it to be little f of xy if the point xy is inside our region D, and it's going to be defined to be 0 if our point is outside that region D. So what we're doing is we're defining this brand new function capital F that's defined on this rectangle R, and the way we've defined it as this piecewise function, if we pick any point inside this region D, well then it shares the same value as the original function little f of xy. If we pick any point outside of region D, well then we're making the value 0. So if we were to graph little f of xy, what it would look like is it would be a surface, kind of, maybe this is an example of one, a surface hovering above the xy plane, and region D here is its shadow. So here's kind of region D. Well, the graph of this brand new function capital F is going to look exactly like the graph of little f on that region D, and then it's going to be completely flat on the rest of the rectangle. And so what we're able to do is the issue here, the question is, how do we calculate the double integral of a function over a general region D? Because when we went through the definition, we had our rectangular region, and then we kind of broke it up into a whole bunch of little sub-rectangles. So it was all rectangle based. Well, the idea is we're going to calculate the double integral of this piecewise function. Because this is something we can do. So because it's defined over a rectangular region. And this is how we actually define the double integral. So the double integral of little f over some general region D is the double integral over the rectangular region R of that piecewise function capital F. And so here, again, D is a bounded region because we have to be able to enclose it with a rectangle. And that's really what we're going to be looking at, is bounded regions. And R, well, that's a rectangle. So that's our rectangle that we've chosen to enclose it. All right. So what is the interpretation of these double integrals? And you might be wondering, we're gonna look at the proof a little bit more for this. But as I'm thinking here, you might be wondering, how can we integrate this? Because this function, piecewise function, is discontinuous. So there's a break in the graph going from this piece down to the flat piece here. And the reason, or kind of the reason here, is because it's only discontinuous on just this kind of boundary edge. And if our boundary edge is nice, in this case it's a nice curve. If the boundary curve is nice, kind of the size of that curve, if we're thinking of area, the size of that curve, if we measure it in area, would be 0. So the edge here of our boundary isn't going to really influence or have an impact on the volume that we're calculating. And that's really what we're doing with when we think of double integrals. We're thinking of them as volume. So we can look at the volume sitting underneath this flat portion. The volume would just be 0. And then we can look at the volume sitting underneath the original graph. And the edge, because the area, the size of that edge is 0, the area would be 0 for just that, in this case, that kind of circular looking part. It's not going to contribute to the volume anyways. So we're able to kind of not worry about that boundary curve in this case, if our boundary curve is nice. So we'll see that a little bit later. But again, we want to interpret these double integrals as volume. So how do we interpret this double integral? Well, if our function little f of xy is greater than or equal to 0, we want to think of this as the volume under the graph. So we want to think of it as measuring the double integral as measuring the size of that amount of space in between the graph and the xy plane. So this is our interpretation of our double integral. Now, if our function little f of xy is less than or equal to 0, so the graph is underneath the xy plane, well, then the interpretation is that this is actually still measuring the volume, but it's the negative volume. So the double integral in this case would be equal to the negative volume. And the last possibility is maybe we have a function, just a general function, little f of xy, that's both above and below. So we have a function that takes on both positive and negative values. Well, in that case, the double integral is measuring the net volume. So it's telling us how much, it's the volume that sits above the xy plane minus the volume that sits below. So if our function is positive, then it's just the double integral calculates the volume. If our function is completely negative, well, then it's the negative volume. And if our function takes on both positive and negative values in our region, well, then we're actually calculating the net volume. So it's the volume above the xy plane minus the volume below the xy plane. All right, so our region, we're going to be considering primarily 2 types of bounded regions. So we're going to start by looking at the first type. We're going to call this type 1. Don't really worry about the names too much. So we say our region D is said to be type 1 if we're looking at the points xy in the xy plane. X is between 2 constants a and b, and y is between 2 continuous functions of x. So in this case, the x interval is in between two constants. And the y interval is in between two functions of x. So how this would look is, if we're looking at our region, how would something like this look? Well, we have our xy plane, and we have our region D, and the x coordinates are kind of giving us all the x values for points in this region. They fall in between two vertical lines. So this would be x equals A, and then this one would be x equals B. So all of the points, all of the x coordinates fall in between two vertical lines. Now, all of the y coordinates for points in this region, though, they're not in between horizontal lines, so we don't have a rectangle. We kind of have it like a distorted rectangle. And so the y coordinates fall in between two functions of x. So we have our top function, which is the bigger one, and then we have our bottom function, which is the smaller one. And that's the way we kind of want to think of this. We're going to want to be able to identify the top function and the bottom function to help us kind of pick out what's going on with our region. And so how we're going to calculate our double integral then is that if our function is continuous on the region D, well, we're able to write it as an iterated integral where the inside integral, use blue. So when we set up the inner integral for this iterated version here, we're going to be integrating between these two functions. So our y coordinates now are going to be in between two functions of x. So when we do this inside piece here, when we're looking at the integral from g of our bottom function to our top function of f of xy dy, when we do this iterated integral, only x terms should be left when we're done. So we identify, for these regions, we identify the top and bottom functions, and then we set up our limits of integration with those top and bottom functions. And then the intervals for x, well, those are just going to be constants. So we're just going to throw the constants in for our integration for x. So let's see how this is going to work. And we'll look at the proof. Well, we'll see if we have time. If not, we'll do it in class. So let's look at example 1. So we're going to do the double integral of the function x plus 2y, where D is the region bounded by the parabolas y equals 2x squared and y equals 1 plus x squared. So we have to be able to picture what this region D looks like. So let's look at it. It's the set of points xy such that, and we want to graph these two functions or be able to picture what they look like. And in this case, we've graphed the function y equals 2x squared. We've graphed the function y equals 1 plus x squared. And we notice that they actually intersect here. So we're looking at this region that's bounded by the two parabolas. So this is our region. It's bounded in between the two parabolas, extending out to those intersection points. And we see that the intersection point on the left here is -1. Happens when x is equal to -1. And the intersection point on the right happens when x is equal to +1. Now we could figure this out algebraically by setting these two functions equal to each other and solving for x. So that's going to give us the x inequalities, we see that this region extends from intersection point to intersection point, so from -1 to +1. So when you do this, you might actually have to figure out the intersection points. We kind of did it just by looking at the graph, but we can do it algebraically as well, by just setting the two functions equal and solving for x. All right, so now we also have to figure out the inequality for y. And so when we look at this, we want to kind of draw to kind of help with this, we want to figure out the top function and the bottom function. So what's our top curve? Well, our top curve here is this parabola with the +1 in it, because we've started at the when x is 0, we've started 1 unit up. And then our bottom curve is the 2x squared. That one's lower on the page. So we have our top curve, and then we have our bottom curve. And we're looking at the region sitting in between those two curves, going from intersection point to intersection point. All right, so the top curve was 1 plus x squared. So when we set up our y inequality is going to start with the bottom. So the bottom curve in this case was 2x squared, and then our top curve there was 1 plus x squared. So we have our y inequality. And now we're ready to set up the iterated integral. So we're going to do the double integral of our function x plus 2y. And we're going to write this as an iterated integral, where the last thing we do is the x and the first thing we do is the y. So our y terms here are going to go from 2x squared to 1 plus x squared. So we're just using our inequality here. And then our function is x plus 2y. And we just have to make sure the differentials and the limits of integration match up. So the first thing we're going to do is this inner iterated part, the inner integral. A lot of I terms. It gets a tongue twister. So the inside integral here, that's our integration with respect to y. And then once we're done with that, then we'll finish off with the integration for x. So you just want to make sure for these types of integrals, the variable limits of integration should be on the inside, and then your differential should be the differential for the variable we're looking at. All right, so now now we're ready. Get the antiderivative here. So the antiderivative of x plus 2y is xy plus y squared. And then we're evaluating this from y equals 2x squared to y equals 1 plus x squared. And then we have our dx there. Now when we plug in, the top number gets plugged in first. And so when we do that, we're going to end up with, again, we still got to keep writing this integral sign. But let's take the top number and plug it in. So we're going to get x times 1 plus x squared plus 1 plus x squared squared. So all I've done is wherever I saw a y here, I plugged in the 1 plus x squared. Okay. Well, then we subtract, and then we plug in the bottom portion, just like doing a regular definite integral here. And so we plug in, and when we do that, we get x times 2x squared plus 2x squared squared. And then we're going to have to simplify this down as much as possible before we try to do the x integration. All right, so all we did is we looked at where we had a y term. And when we plug the top number in, I replace those y terms with 1 plus x squared. And when we did the bottom term, I replaced those with 2x squared. So our bottom curve and our top curve we plugged in. All right, so now we want to simplify this down. All right, so let's multiply things out. So over here, we're going to end up with x plus x cubed plus 1 plus 2x squared plus x to the fourth. When we multiply all this out, then we're subtracting, and we have a 2x cubed plus 4x to the 4. We keep simplifying this down. And what can we combine here? Well, we got an x to the fourth and an x to the fourth, so we can combine those. So we're going to end up with negative 3x to the fourth. Then we have an x cubed and a minus 2x cubed, so we'll have a minus x cubed. And then we got, well, a 2x squared, and that's the only x squared term, so plus 2x squared. And then we have a plus x, that's the only x term, so plus x. And then we have a plus 1. So we get our function all simplified down, and now we're ready to get the antiderivative. So the antiderivative for x is negative 3 over 5 x to the fifth minus 1 over 4 x to the fourth plus 2 over 3 x cubed. It just keeps going. Plus 1/2 x squared plus x. And then we're going to evaluate this for between x equals negative 1 and x equals positive 1. And then we plug in. So when we plug in positive 1, we plug the top number in first. So we end up with negative 3 over 5 minus 1 over 4 plus 2/3 plus 1/2 plus 1. Then we subtract, and then we plug in the negative 1. And when we do that, we end up with positive 3 over 5 minus 1 over 4 minus 2/3 plus 1/2 minus 1. So don't forget, when we plug the negative 1 in, all the odd powers are going to keep the negative 1. And then all of the even powers, the negative 1 just cancels out. We're left with just a 1. All right, so we could simplify this down more. I'll leave it for you to simplify that down. If we did get a common denominator, this ends up being 32 over 15. And now, just to pop back up here, our function x plus 2y is, we were able to integrate this function over this bounded region. And just thinking here, is this function positive on the region? It might not be. So it's definitely positive on this section because all the x and y values are positive over there. But I'm not sure if the function's always going to be positive over here. Maybe it is. But in any case, we can interpret this as the net volume. So we want to think of this value here as the volume, or the net volume. And the fact that this is positive is telling me that even if the function does dip below the xy plane, more of the region sits above the xy plane than below. And what we found is kind of the size of the difference there. All right, so this is how we're going to be integrating these double integrals, and we'll get a little more practice, and we'll see the other version, the other type of our region D in class. So we'll see you then. Bye-bye.